Let's move now to a discussion about how we would calculate the rates of change for multivariable functions. And to do this, we use a tool called partial derivatives. And the reason they're called partial derivatives is because since you have more than one independent variable, you actually have a derivative to describe the change in each variable. So if you take the derivative, let's say with respect to x, then you're only getting a piece or a part of the overall picture. You're only getting a partial view of what's going on. So we call these partial derivatives. Now, as we move in the x direction, let's say, we can draw a tangent line to the surface that is parallel to the x-axis. And if you draw that tangent line parallel to the x-axis and measure the slope of that line, then that is what we call the partial derivative with respect to x. So we'll explore this in a lot more detail, but that's the basic idea. It's still tangent lines, it's still slopes, but now when we talk about the partial derivative with respect to x, we are computing the slope of a line that is parallel to the x-axis. If we talk about the partial derivative with respect to y, we're computing the slope of a tangent line that is parallel to the y-axis. So here is a visual representation of what we mean by a measurement of rate of change in the x direction. So first note where the x-axis is located, and we're going to be doing stuff that's parallel to this axis. The easiest way to do this is to actually think about taking a surface like the one you see here. So imagine that this is sort of like a quarter of a cone or a quarter of a paraboloid. And what we're going to do is we're going to cut that surface using a flat metal sheet. And that flat metal sheet is completely parallel to the x-axis. So it would look something like this. You have this metal sheet that comes down, it cuts this surface. You might think of this sort of as a jello mold. It's very flexible. You can come in with a knife, you can cut it with a very sharp knife, and that knife is parallel to the x-axis. Now, when you do this, you will leave a trace of the cut where the knife or this metal cutting surface intersects with the surface itself, with this jello mold, so to speak. And so this particular curve is what's important to us. So what we do now is we simply locate the point on that curve and we draw a line that is tangent to that curve at that point. This is the tangent line T sub x. What's important to notice here is that this tangent line is perfectly parallel to the x-axis, and it is perfectly parallel to that cutting plane, so that line sort of lives in that cutting plane that we use to generate this curve, this red intersecting curve. And what we can do is we can take that intersecting plane along with the curve and the line and just focus on them. So what we do is we simply take them and sort of pull them out. And the advantage here is that we basically have like a two-dimensional picture which we are very familiar with, and we can see very clearly that at that point where the x-coordinate is a, there is a specific tangent line, Tx, and that tangent line has a very measurable slope. So this is what we call the rate of change in the x direction. We will formally call this the partial derivative with respect to x. Before we talk about how to actually compute derivatives with some formal rules, let's talk about notation. There's different kinds of notation that are available to us for a function z which is dependent upon x and y. The first one is somewhat traditional. It looks like a little d for derivative, but it's slightly different. It's sort of what I call the squiggle d because it's got a little sort of curved here. But this is the notation for partial derivatives. If this were a regular derivative in 2 dimensions, it would be a normal lowercase d. So this is how we distinguish the two. So we talk about the derivative of the function z with respect to x. So again, this fraction is really not a fraction. It's more one notation that's telling you two things. On the top, it's telling you that the function that you're dealing with is z, that's the dependent variable, and on the bottom, you're being told that you're taking the derivative with respect to x. The second kind of notation that we have is this subscript notation. We can say f sub x. So the subscript tells you what partial derivative that you're taking. And then a slightly fuller version of this would be f sub x with the two variables included so that you know that x is involved but also y is involved. So it's just a little bit more complete. The notation that I will use in this course is the simplified subscript notation. Since the function will typically be given to us and we know what all the variables are, we don't have to worry about listing all the variables every time we write down the derivative notation. And also the squiggle notation just a little bit cumbersome. So we choose something that's a little bit more simple here. Now, just to summarize what these things mean, let's be really clear here. The partial derivative with respect to x, f sub x, this is the rate of change of z with respect to x. So x is being allowed to change, and we're measuring the effect of that change on the variable z. On the other hand, f sub y, the partial derivative with respect to y, is the rate of change of z with respect to y. So in this case, y is being allowed to change, and we're measuring the effect on z as that change in y occurs. So it's really important that you are really clear on what this notation means and how it all fits together so that when you see these questions, when you see this notation, you'll understand what's being asked. So make sure you study and review that as we move forward. Before we begin to actually take partial derivatives, there's a key point we need to make and keep in mind, and that is that when we are taking a partial derivative with respect to a variable, all of the other independent variables behave as though they're constants. So let's take a look at what this means visually, and then we'll do some examples to see what it means in terms of actually finding the derivatives. So here's what's going on visually. Let's start with a point here in this three-dimensional space. And what we're going to do is move parallel to the x-axis. So if we move parallel to the x-axis, it's going to look something like this. So we're moving parallel to the x-axis, and then when we start moving at this particular point, our y distance is right here. This blue arrow is a measurement of the y distance. Now, if I move that red point along the line, the blue line that is parallel to the x-axis, to a new point, say like to here, then the blue distance from the x-axis in the y direction, the y-coordinate, is still the same. Those two shorter blue arrows are the same exact distance because I have moved perfectly parallel to the x-axis. It doesn't matter how far I go, as long as I stay parallel to the x-axis, like maybe here, the y distance is still the same as it was in the second step, and it's the same as it was in the first step. You can do that as much as I want. Those y distances will always be the same, and therefore they're constant. So if I'm taking the partial derivative with respect to x, then I'm traveling in the x direction. That's what that means. And when I do that, the other independent variable, y, stays constant. It's going to behave like a constant. So that's what's going on visually, and that idea is very key when I am taking partial derivatives.